you see this?
Yes.
Yes.
Yep, we got it now, Bill.
Bingo.
If you can read that, I'm not going to touch another button other than advance the slide. Here are our officers. The only message here is in both groups we are term limited. So we need new officers for next year. Start thinking about stepping up. Because if we can't get officers registered with IEEE, this will stop. And that brings us to tonight's meeting. Fusion energy, clean and inexhaustible, Dr. Raymond L. Orbach. And Kai, did you want to take over the introduction from here? Okay. I'm going to.
Welcome, everybody. This is.
Kai, you're muted.
Oh yeah,
You're muted.
So maybe I share my screen.
Now we can hear you.
Okay. Tonight's speaker.
I need to unshare my screen.
Yeah. Okay.
Stop sharing. Okay.
All right. Good. So I'm going to share my screen. I need to go to that page that I want to. PowerPoint. Okay, so this is the so welcome to the tonight's meeting. So we have four other line member chapter as a co-host from Dallas, Fort Worth, Houston, and there's one more one, Galveston. So mostly all Texas based. Also Colorado, Denver. So tonight's speakers, actually my next door neighbor, Dr. Orbach, and he's a current professor at UT, but he has a illustrious career. He graduated in 58 and gets PhD in 60 from Berkeley. Then he would teach for a number of years. Then he joined the government as a chief scientist of the nation. So he joined the W. Bush years 2002 to 2009. And 2006, he became the undersecretary of the Energy Department. And he talked to President Bush a little bit more than the other secretary on some technical part of programs. So he's going to talk to you about the fusion energy and also one of the important programs during that year, IEEE. So I'm giving you Dr. Albrecht. Yeah.
Well, thank you for bringing me here. Very pleasure to talk to my colleagues in the science and engineering.
No audio.
You still muted?
No, shouldn't be. Kind of talk.
Oh, sorry. I'm talking that where I'm going.
Still no audio.
Can you hear me now?
Nope.
Are we on mute?
No, it's not. Okay, go
How
ahead.
about now? Can you hear me?
Not very well.
Let me get closer.
Kai, what mic do you have? What I mean, you had a mic on, Kai? What?
Yeah, the mic's on. Yeah.
Might just
I
be
can't
your
hear you. I can't hear
proximity
you
to
right
it.
now.
Yeah, how about if I talk right now?
There we go.
Perfect.
That's what you got to do.
Yeah, I'll talk directly into the computer. Well, again, if you missed what I said before, it's a great pleasure to be here with everyone and to share some of my thoughts about future energy. I don't have to tell anyone on this message about the need for clean and unlimited energy that would be an ideal for our planet. And I think it's fair to say that fusion probably comes as close to that limit as you will find. And so I'd like to talk to you today about how it came about, how the fusion program originated, what it is, and what the prospects are for the future. And I begin with our sun, which, as you well know, is there because of condensation from a gas cloud that, how do I advance it? Oh, okay. About 4.5 billion years ago, there was a cloud of gas, huge cloud, that we now identify as our sun and solar system. A large amount of matter at the center gathered together and became increasingly hot as gravity caused it to collapse. The rest of it, as you well know, flattened into an orbiting disk, and then individual planets and moons and et cetera formed from that gaseous cloud into what we now call our solar system. The central mass is our sun, and it's powered by thermonuclear fusion. The sun generates its energy by forming a helium product as a consequence of fusing hydrogen nuclei together. The sun is so hot that the electrons are basically ionized, so you can think of it as a plasma. In its core, and this is really remarkable, the sun fuses about 620 million metric tons of hydrogen each second. So it'll give you some idea of the amount of energy that you can generate from fusion itself. And the process of fusion in the sun, which we really need to go through because that's the basis of what we're trying to do here on Earth, is called the proton-proton chain. It starts with protons, and as I said, ends up producing helium and a lot of energy. Because the total mass of the helium that's produced is less than the mass of the protons that went into it, there's excess mass, which is formed, as Einstein told us, into shear energy, namely E equals mc squared. So what you have then is an example of how fusion creates new molecules, but also creates vast amounts of energy. Now, the way the sun works is two pairs of protons fuse, forming two deuterons. A deuteron, as you see here, has one proton and one neutron, and is an isotope of hydrogen. The issue associated with that fusion has to do with the temperature and gravitational forces in the center of the sun. They're sufficiently large. Remember, the protons are both positively charged, that they repel one another. But the kinetic energy associated with the temperature and pressure is sufficiently high that it overcomes what we call the Coulomb barrier and allows the two nuclei to fuse. Now, a deuteron fuses with an additional proton that gives you a charge, nuclear charge of 2. Yes? Is there a problem? Sorry, I can be interrupted at any time. And you form helium, which has 2 protons and a neutron.
Oh.
And then 2 helium nuclei fuse to create beryllium, which is unstable. And so it disintegrates into 2 protons and a helium atom. And it's the helium that we know, namely helium-4. And it's about as stable as these noble gases get. It also releases 2 neutrinos, 2 positrons, and gamma rays. It also releases a huge amount of heat, which of course is what gives us the ability to survive on our planet. Now, I would like to talk about what we can do on Earth. First of all, we cannot reproduce the pressures at the center of the sun. It's just not practicable. We can, however, generate very high temperatures. And the high temperatures create enough kinetic energy that you can overcome the Coulomb barrier. But the Coulomb barrier, it turns out, for 2 protons is huge. And the same would be true for 2 deuterons. The smallest barrier that you have concerns 2 isotopes of hydrogen, namely deuterium and tritium, which has another neutron besides the one that is there for deuterium. And this turns out to have the smallest threshold. Now, the problem is that tritium itself is unstable, has a lifetime of around 14 years. But nevertheless, if you could produce tritium in some controlled fashion, deuterium is very plentiful. As I'll show in a moment, the amount of deuterium in Lake Erie alone would serve to produce the energy that the Earth would need for 10,000 years. We're talking about a lot of deuterium. So deuterium is plentiful. Tritium is not, because of what I said, namely a short half-life. But if you could fuse the 2 together, you would get helium, energy, as we saw before, and a neutron. And this is the heart of how we could control fusion on Earth. That is, if somehow we could get a plasma sufficiently high, say around 100 or 150 million degrees Celsius, and we could somehow contain it and have enough tritium and deuterium within it, the only thing coming out of the tailpipe is helium. And if you don't like helium, that's not a problem. Lighter goes off into the atmosphere. We can't. Gravity is not strong enough to hold it very long, and so there's nothing but energy and that neutron. And we will see the role that neutron plays in just a moment. But the point is that if you could harness it, if you could make this work, you have something that has no environmental impact and yet produces a huge amount of energy from a source, deuterium, which is so plentiful that you can get it out of seawater without any trouble. So that's the dream. That's what we're after. Can we, in fact, create this process in a controlled fashion and at such a magnitude that we can actually power the energy needs of our globe? Now, the first problem is, how are you going to contain something that's 200 million degrees in temperature? If it hits anything that you can think of, even the hardest material that you can imagine, it just will destroy it. It will melt at those temperatures. And so the Russians invented a configuration which actually controls this very hot plasma, and in principle would allow you to create these huge temperatures and not ever touch a wall. And it looks a little bit like a donut. It's called a tokamak. And I've given you a picture here of what one looks like. You have fields, those rings that you see, and those magnetic rings create a current in the plane interior of the donut that just goes around and around. So it traps a plasma or a ionized gas, and with luck, you could design it so that it doesn't hit the walls of the tokamak. And that, of course, is the big problem. How do you actually create a stable plasma at 200 million degrees that has enough density in it that produces power of the sort that we want? This is not a new dream. This dream has been around for almost 100 years. But the last, I would say, 20 years have been a renaissance in fusion. And those of you in the investment community know that there are just a lot of startups now that are trying to produce controlled fusion. I'm going to talk about the biggest. It's called ITER, which used to stand for International Thermonuclear Experimental Reactor. But every time you say the word thermonuclear, people panic. And so all that you know today is that it's called ITER. And it turns out in Latin, it means the way. It is huge. This one doesn't have a man on it, but if you look at the lower right-hand corner, the man would be about the height of those little, at the center, those little rings that you see. It's immense. And it has to be because you want power out. And that means you've got to have a lot of stuff inside. Now, this is a cutaway picture of ITER. You will notice that there's a hole in it. That's that donut, but the hole is not round. The hole is a D-shaped. And the fact that it's D-shaped turns out to give you the stability that you need. And ITER, again, is not new. It was started in Reykjavik when our president and the Russian president were unable to agree on a nuclear pact, but decided they had to have something to show that the meeting was worthwhile, announced a joint program for controlled fusion. That was in 1988. The United States was a party to that. We joined 3 other countries, but in those days, the cross-section was circular. And after about 10 years in 1998, it became clear that it was unstable, that you couldn't control it. And so the United States withdrew. And so ITER then was carried on more or less as a theoretical concept until the early 21st century, which is actually where I came in and the Department of Energy entered. But this is it. You'll notice there's all kinds of pipes and so on. This has to be cooled to liquid helium temperatures. Remember those magnets that you can see them, you can see those buses around that D shape. Those are coils, and the only way to generate enough magnetic field is to have a superconducting coil. And to have a superconducting coil that can carry enough current, you've got to have very low temperatures, namely in the liquid helium range. And so this whole thing sits inside of a cryostat. You might say this is really out of the world, but it exists, and I'll actually show it to you as we progress. In any case, a lot of those pipes that you see going into it are feeder pipes to feed in the gases and also to detect what's happening inside, namely, is fusion taking place or not. You will see, you can't see it actually in this cutout, there's a lot of energy that's being produced, and it has to get out during the experimental phases. And so there's a lot of study right now about how to handle the gases as they leave the controlled fusion process. The whole idea is to create enough heat that you can create steam and drive a generator which produces electricity. That's how a fission plant works. This is not fission, it's fusion. There's no radioactivity outside the machine. Let's go back. If you look around the D, you will see a lining around the inside of the D, and that's called the blanket. And it's the means by which the gases through a heat exchanger then are heating whatever liquid you're using to drive the generators. But it also performs another function, and we will see what that function is. Remember that neutron? That neutron strikes the blanket, that extra neutron in the fusion process. If I had a layer of liquid lithium, lithium is a very common element. We know it now from batteries. If I had a layer of liquid lithium on the surface of the blanket, when that neutron hits it, it produces tritium. And so the whole concept then is based on that one neutron. And you've got to conserve it because you produce one tritium for one neutron. You don't want to lose any neutrons. But if you could develop a blanket that would absorb every neutron, you could produce the tritium, which then would combine with the deuterium gas in the center of the toroidal structure and give you fusion. So even though tritium is rare and slightly radioactive, it doesn't matter because it's fused with the deuterium to give you helium and another neutron and energy. That's the concept behind ITER and almost any other plan for controlled fusion. As I say, the stuff out the tailpipe is just helium. And if you don't like helium, no problem. It just goes off into space. Another nice feature about a fusion energy source is that if something goes wrong, you just turn off the power because the whole fusion process depends on that temperature and you have to heat it somehow. And goodness, but oh, I'm going the wrong way, sorry. You just turn it off, the gas becomes cold and everything just stops. So it's not like a fission reactor where if something goes wrong, you've got a real problem, as we saw in Fukushima, for example. So it has an advantage of control. And as I said already, there's enough deuterium in a body of water the size of Lake Erie to provide all of the energy the Earth requires for 10,000 years. So this is big stuff. And if we can only make it work. Now, at a meeting actually before Reykjavik, Reagan was already interested in exploring fusion energy. And then in 1986, they agreed, when everything else failed, to have a joint program for fusion. And as I said, in 1988, the conceptual design activity began. It actually began at the University of California, San Diego, which was the site of ITER conceptual design activity. However, in 1998, we felt it wouldn't work and we left. And so ITER then was left to those three countries that had started it with us, but it was really off the burner. It was really static. However, people were well aware of the promise of fusion. And so the House of Representatives in 2001 required, actually forced, and believe me, when the appropriators tell you to do something, you do it, the Office of Science to take a number of actions that would explore a burning plasma experiment. A burning plasma is a way of saying that it's self-sufficient, namely that the gases and that neutron that produces the tritium are a steady state. The energy that's produced entirely comes from the plasma itself. Well, I became director of the Office of Science in the spring of 2002, and I had congressional action to start looking into it. So I commissioned a study that was held actually by the fusion community in Snowmass, Colorado, which was really the beginning of ITER as we now know it. We had a fusion energy advisory committee to look at the plan that the Snowmass meeting produced. Remember that you had a lot of laboratories exploring fusion energy, and the last thing they wanted was to lose the money for their research. And yet they all came together and unanimously supported the United States rejoining ITER. It was, I thought, a wonderful demonstration of integrity of the scientific community. I won't go through all the details. I asked finally the National Academy to evaluate the Snowmass report, and they endorsed it. And then I was able to have the President of the United States say that this following. Well, I won't read it to you. Basically, the results of ITER will advance the effort to produce clean, safe, renewable, and commercially available energy by the middle of this century. George W. Bush was wonderful. He understood the importance of energy, and he understood that he even predicted actually when it might take place, namely in the middle of this century. And we welcome the opportunity to work with our ITER partners to make fusion energy a reality. You can't imagine how wonderful those words sounded to those of us working on the project. As a director of the Office of Science, I put together a facilities plan for the future of science, a 20-year outlook in 2003. And we prioritized 20 large-scale scientific facilities, and guess which one was number one? ITER. And people ask me, well, what about all the high energy physics and all the other things that physicists do? Why are you talking about ITER? And I simply said, we're an energy agency. That's our job. And this is long-term and experimental, but that's what the government can do at this scale. And so it became the number one priority of the Department of Energy. As soon as we rejoined ITER, the European Union, Russian Federation, and Japan, those three had stayed after we had left, welcomed us, but then China, South Korea, and eventually India joined the collaboration. Now, just a few words about how you put something like this together. There's money involved, big money, billions, and we had to have a partnership. And I was chosen to head the negotiating team for the United States with my colleague, Todd Harding, and then fortunately, somebody that knew something about international law, Melanie Khanna from the State Department. And we were charged with making ITER work, at least getting it started. I won't go through all of the details. You can actually, I gave them to Kai as a background, but there were 4 sites that were considered for putting ITER. Remember, this is a multi-billion-dollar facility. The best site was in Canada because that's where they produce tritium. The next best site was Barcelona, The third best site was the northern part of Honshu, Rokoshimura, and the worst site was the French site. So guess which one won? The French site. The largest coils had to be made on site because it wasn't a seaport. They required construction then of a factory. Have you ever driven in Provence? Those roads are tiny, and you saw the size of Ytre. The coils wouldn't fit. They had to actually destroy a bridge and recreate a highway from Marseille, where the material was delivered, into the site. I won't go through all the details, but well, it was political. Do I talk about that? No. It was political in the following sense. We had a Spanish site, a Japanese site, and a French site. The Canadians refused to join. They didn't want to put any money into Ytre, which I think they probably now regret, but that was then. The Spanish and French side are part of the EU. And who controls the EU? France and Germany. And France and Germany said, Cadarache is a wonderful place. We had visited the Spanish site near Barcelona. It's right on the beach. It has a nuclear license. It would have been perfect for it, but we're not France and Germany. However, we suggested that the best site was in Japan because it has a port. You could put the biggest things that you needed to ship on a barge and just put it in. And so we reached an impasse. Namely, 3 of the 6 members favored Japan and 3 of the 6 members favored France, favored Cadarache. In the event, I won't tell you about all the details that happened in between. The EU and the Japanese reached an agreement, namely that the EU would choose the site, but that a large part of the EU responsibilities would be transferred and paid by the EU to Japan. So it was an agreement. The agreement said that the first director of Ytre would be Japanese. And so the Japanese backed out and it ended up in Cadarache. And that was very unfortunate because the Japanese director was a disaster and it set back the construction of Ytre. And whenever you set back a construction project, costs just go up. This is a list of the members. We had to actually create out of whole cloth an international agreement. When you create an international agreement, you're dealing with 7 different countries, the EU called it a country, 7 different parties, all of which have their own legal structures and their own demands. We had to negotiate that. It took almost 4 years to fill the negotiations. The final signing was in 2006. We started this in 2003. And those 3 years were just nothing but hell in terms of negotiation. Just to give you an example, we weren't trusted. The EU said, how can we trust the United States? We want a treaty. If we had made Ytre a treaty, we'd still be waiting for the Senate to approve it. I can give you example after example where that good things have just never surfaced again once they went into the Senate. So we wanted what we call a presidential agreement, but the EU said, how can we trust you? And we said, you have to trust us. Well, remember what Reagan said, trust but verify. The EU said, no way. Finally, we worked out language that went around that. For the United States, for example, we the issue of privileges and immunities, something you probably never think about, came up. And the EU said, we don't trust you. That means that somebody who's working for ITER, if they come to the United States, they're protected like they would be in a consulate or in an embassy. They can't be taxed. You can't arrest them. Their family is protected and so on. Well, we actually have an IOIA, which is an agreement that it's what we use for embassies and so on. And the administration included ITER as a part of that. So that's how we solved that problem, but that wasn't enough for the EU. I've given Kai a write-up of all of the things we went through, and if you're interested, you can follow up on that. This is the signing agreement in the Elysee Palace. I'm the second from the end on the right, and that's Jacques Chirac, who's the president of France, because remember, it's being built in Cadarache in the center. I don't know if you've ever seen pictures of the Elysee Palace, but it's a palace. I mean, it was quite an event. And there we were, all of the representatives from the different countries. This is what ITER looks like today. This is literally off the web from 2 weeks ago. And you see that central building. You see all of the infrastructure around it. It's well on its way. And they will have the first test of the burning plasma around 2035. Now you can say, wait a minute, that's still 10 years from now. Yes. The tritium will be flown in from, remember that Canada site? They produce the tritium because we don't have the blankets yet. They're still working on that design. And there's a French Air Force base next to Cadarache. So it'll be flown on pallets into the French Air Force base and transferred to ITER. The deuterium is no problem. They have that's not an issue. And one of those ancillary buildings there is a building to build the coil, because you can't transport it over those Provence roads. Let me finish. ITER will do the following. It will achieve a deuterium-tritium plasma where the fusion conditions are sustained mainly by internal fusion heating. That's what I talked about when I said burning plasma. It will reach a temperature of 150 million degrees Celsius. Now, the stability in that D shape is still something we're not entirely comfortable with. That's why the E, ITER, stands for experimental. We are going to experiment with different structures for the plasma to keep it away from the wall. It will, in 1935, have a Q of 10. That means the plug energy, the energy from the wall, as we put it, will be 50 megawatts, and it will produce 500 megawatts. The Q, if there were no net production, Q is 5, and that has to do with the internal dynamics. So Q is the quantity you're after, that ratio. In the laboratory and these small tokamaks in JET, for example, in England, they have a Q of about 0.5. And that's the highest Q that's ever been produced on Earth. So we're 10 times or more that Q at ITER. The first plasma, as I said, will be the deuterium-tritium burn will be in 2035. A demonstration power plant called DEMO is the next step. And the plan is that if, in fact, they can get Q equal to 10 in 2035, a parallel process is being pursued to produce a demonstration fusion reactor. It probably will not be a tokamak. It won't be a donut-shaped tokamak. It'll probably be a spherical tokamak. Just imagine that center just goes down into a narrow pipe, and you have a ball. That's called a spherical tokamak. But they have to learn about how to make that blanket, generate tritium. They have to learn how to get the heat out. There's a lot of ease there, a lot of experiments that have to be done. If DEMO works, and there's every reason to hope that it will, we'll be able to put electricity into the grid in 2050. Now, it's something that the Earth, if you look at the IPCC reports, the Earth desperately needs. We are now heating up. The temperature of the Earth, as we know it here in Austin, continuously goes up. The amount of CO2 that we produce continuously increases. If we don't do something, we're going to get in big trouble. And so ITER, we believe, is the answer to that. And hopefully it'll be mid-century. I want to thank everybody, and I'll be glad to answer any questions. The stellarator, the question is, what do I think of the stellarator concept? The stellarator is a wonderful design. It looks like, remember that donut? Just imagine you twisted it so that it looks like a twisted donut. I guess there may be somebody may make donuts like that. And the beauty of it is that from the perspective of the plasma, it's completely contained. The Germans have built now actually a demonstration stellarator. It's huge. I think it must be 50 meters in diameter or something of that magnitude. Don't hold me to that, but it's very large. The problem is the geometry. You have to have this very complex twist in the ring to actually get it stable. And nobody has figured out yet how to do a controlled fusion. Sorry, no one has figured out yet how to do a controlled fusion program. They are, in fact, going to create a deuterium plasma in it and see if they can contain it if it works. In principle, it's a wonderful design because it doesn't need, it doesn't have the stability problems that you find in a conventional tokamak design. And so we'll see. There are a lot of examples of experiments trying to produce controlled fusion. As I said, in the United States, there are a number of facilities actually that the private sector is funding startups. I don't know how many of them will succeed, but the more the merrier, because we learn from each of these experiments something about how to control a plasma. Is there a breakthrough to accelerate the process? I wish there was. Just remember, just to build ITER, I think it's north of 18 billion now, the cost, and it's shared by all the parties. Although the EU plays, because it's cited in the EU, they pay about 40% of the cost, and the rest is divided equally among the other parties. It's a scale issue. Namely, you can do things in the laboratory that have promise, but can you get a Q of 10 whatever, and really produce enough energy to make it worthwhile? The jet, as I said, had a Q of about 0.5, and they used tritium that they were able to get from Canada, and now it's been decommissioned. So there's not another big machine that I know of. There are a lot of smaller ones. For example, the MIT design is a very interesting one where they use huge magnetic fields. I mean, I can't remember what they are, but 20 or 30 Tesla that reduce the size. So you don't need something that big. Whether it can scale up, I don't know. So right now, we'll take anybody that comes along and try and help them. The budget for ITER from the United States is about $240 million a year. That's cash that goes to ITER. Now, it turns out a large part of that cash is actually spent in the United States because we're producing the coils and some of the magnetic structures for ITER. But that's a lot of cash. The budget for fusion in the United States is of the order of 800 million. And that goes to fund the experiments at Princeton, for example. There's a Princeton Plasma Fusion Laboratory that is a DOE lab, one of my labs actually, when I was in DOE. And it's the primary large-scale laboratory for the United States. And they're doing wonderful studies about stability and so on. But I don't know, I mean, it's a question of size and scale. And I hope the MIT design works. I mean, it's not as though we don't want it to work. Any idea that works would be wonderful. But my money's on ITER. Not just my money, your money too.
2050, if it comes to pass, in the current environment, it's more likely to get defunded than continue to fund it.
Well, I mean, 2050, as people have said about fusion, it's always 50 years off. And I think now this is 2024, it's less than 50. So we may be converging. The frustrating thing for me is that I was there at the beginning and I won't live long enough even to see the first burn. So that's the way science goes.
I have a comment to make.
Sorry.
This is Biram.
A couple of comments and questions online.
Okay. Maybe let's answer. Nice question.
Just curious as your thoughts on the initial fusion experiments for laser implosion.
Yes,
It seems like that's kind of.
there is. The question is, what do I think about inertial fusion? The Livermore experiment on inertial fusion was finally able to get a burn. They finally were able to get the little pellet to actually fuse. The way it works is that you have, just think of this room, multiply it by 4. That's how many lasers they have, glass lasers that produce this huge amount of energy in a beam that's focused down on a little particle. I think the size may be classified. I don't know. I don't want to say what the size is because I don't remember if it's classified, but a tiny little particle. And they were able to get more energy out of that little particle than, they were able to get energy out from a fusion process. The problem is that if you talk about wall energy, you've got to provide that energy for those lasers. Now, those lasers are about 1% efficient. And so the people at Livermore said, look, we're dealing with lasers that are last century lasers. if we were able to invest in a new laser structure that's more efficient, we could bring it closer to production levels. The idea would be that you would take these little the little dots and just have a continuous stream, and then you would be hitting the particle with the laser beam as they pass through this hologram or whatever it is that you have around them. I don't know. I mean, when you have 1% efficiency in the laser, you're dealing with laser efficiencies, and I just don't know whether they can actually get to a point where the wall energy get to Q, to get to a Q of 10. But that's a work in progress. I don't want to say anything more, but you can just, I suspect, get a little taste of skepticism in my voice. Yes.
I want to make a comment.
Yeah, please.
So first one from Robert.
Right.
Well, that's a wonderful question. Did everybody hear it?
No.
Okay, the question is, the fission power plants are notorious for cost overruns. In fact, as you well know, there are only a few that still are on the table. Actually, one just started to work. There will probably not be any very large power plants built of fission design because of that cost. One of the difficulties with ITER was project management. And indeed, you may remember I made a comment about the earlier stages of it. To be honest, it took the Americans who are on the council that controls ITER to bring modern project management skills to ITER. And we now have a design, and I think it's fair to say that that process can be controlled. The reason that you have these cost overruns for fission, a lot of it has to do with the shielding. The issue on radioactive contamination, I have to say, I think is way overdone. But the amount of steel and concrete that goes into a fission plant is immense. And you don't need that for ITER or for DEMO, for what I said before. There's no radiation that comes out. The only radioactive material, the tritium, is produced inside the plasma. So the only thing coming out of the tailpipe is helium. So you don't need the protective shield that I think drives up the cost so much for fission reactors. There are these new modular reactors that are coming online at the 50 megawatt, maybe 100 megawatt at the most. And they have a design that will really alleviate a lot of the cost issues. So my guess is that you'll see a lot of that for fission in the future.
I think that's a question from all of you.
Can I ask you a question?
Please.
Yeah, so copper should not be produced anymore in the world, huh? I'm trying to be facetious because copper artificial intelligence is coming and everything is coming in the data centers and all that. So we should not be running after copper then, huh? This
Well,
is just a facetious comment, right? Go ahead.
I understand. I think when one really needs to take a step back and
Sure.
look at the energy requirements of the world. And we have a lot of the world still living in poverty, and they want out. They want to live like we do. And the numbers, they may be capped because of the drop in baby births, but you know, they're going to be of the order of 10 billion in the not too far future. How are you going to provide that? And you can argue that renewables are a way to go, but the amount of surface area that you would need to provide enough energy for the human beings on this earth is just not practical in my view. So you really are stuck by it. I mean, if you want to burn fossil fuel, that's fine. And certainly right now we need to, but you produce CO2, and trying to contain CO2 is not something that currently is very feasible. Okay, I mean, there's lots of ideas about burying it and so on, but we're talking about the energy needs of the world. And to me, the reason I put ITER as number one is that I couldn't think of anything else that would meet the social requirements of our planet down the road, or even now. So 2050 sounds like a far time away, but on, you know, normal scales, that's not an awful long time. It's only 25 years from now. Will there be a breakthrough that will shorten everything? That would be wonderful. But that's a miracle, and if you depend on miracles, you may be disappointed.
So you're debating between two options, fission and fusion, basically. And
Yeah.
what is the impact on artificial intelligence on the economy of the world? I mean, China is making artificial intelligence, India is making AIs and all that, and all that.
I'm
Rush.
pretty familiar with AI, and
Right. Okay.
I work on large data sets myself, and I think it's a wonderful way of working with data. I'm not sure that it's going to, it'll improve efficiencies. There's no question about that. And that's very important. But will it be able to think on its own? I'd like to see that actually demonstrated. I mean, I know people are talking about how awful AI will be and the danger it is to everybody. I think the real danger is the nonsense that may get built into AI if we're not careful. But data sets can speak for themselves, which is what AI is. But are they any more than the input that we put into them? Maybe they're just very clever at taking what we put into them and coming up with something. But do they think for themselves? I don't think so.
Let me explain something about AI, because I'm not an expert in AI. But
Oh,
AI is called large language models. And large language models just talk amongst themselves too. It's like verbose people. They talk amongst themselves and try to impress the listener that they know a crap, but they don't. I mean, I'm just making a similarity argument, that's it. AI is basically that large language models, and data centers is creating much more headache on the environmental part. Data centers are. Everywhere there's a damn data centers in these United States. So anyway, and you agree with that?
yeah, you're going to need a power plant every time you have a large.
Exactly. Yes, that's true. Anyway,
By the way, that's, I think, an argument for the modular reactors. You can put one practically next door to a data
Yes.
center, they eat up a huge amount of energy. They're actually talking now about not having enough electricity to power the
Yeah.
data.
Yeah, exactly, right. Yeah. Okay, thank you for your.
Thank you.
Bob has a question here. How does the work proceed? Sounds like a very challenging project for a long time. What are some of the steps that are being considered?
I missed the very beginning of that. I'm sorry.
Start, maybe you want to.
I was just trying to get the idea. I mean, this is a massive project, and I'm trying to say, are we trying to build? I mean, I'm trying to envision what some of the steps might be. I mean, are we trying? I mean, what kinds of are we trying to build the whole thing? What are some of the next steps in the experimentation process to get there? I mean, it seems that they're trying to build, getting something to all that temperature at one step. That's kind of like end game. What are some of the steps along the way that are being taken for all this funding?
I think that's an excellent question, and indeed, those steps are laid out. That is, there's a series of steps. Remember, I said that the tritium deuterium burn would be 2035, but before that, as soon as they can put that thing together, they will just do a regular plasma burn. That is, they will just see whether they can heat it and whether it's stable. The plasma itself needs to be formed into a shape that's stable on long times. Remember, you're talking about a power plant. You don't want something that works for a millisecond. And so you need the shape, they call it an H shape, for the plasma itself. And by the way, that may not even be the one they finally end up with. But one of the things they have to learn is how to shape the plasma so that it's both stable and doesn't hit the wall. And the way to do that, at least initially, is not burning, but to get a plasma hot enough to mimic what you would be getting in a DT burn. And there are diagnostics that go with it of all sorts that tell you something about what's going on. So there's a period of at least 10 years before they do the burn, where they have a set of experiments, just exactly as you said, that would lead them, so assuming they work, to the burn stage. But exactly, this is experimental. Remember that E in ITER. I keep telling people that this is an experiment. And on the other hand, it's a very important one. And then once you get the burn, that burn will, remember, it depends on bringing the yttrium in. Sorry, the yttrium, bringing the tritium in. But that's not a way to get a power plant. You've got to get the blanket to produce it. So that's yet another step in the process. Now, what they're doing at Princeton is working on the blanket. They're trying to figure out if how much you need and whether it can work. There was a question that was just raised about how you actually get the electricity out. And that poor blanket has got lots of jobs. It has to produce the tritium. It also it has to be a heat exchanger because the heat hitting the thing is hot. And that neutron is hot as well. So that the blanket will be at high temperatures. Remember I said a lithium wall? Why did I say liquid? Because it's so hot that lithium itself would melt. And so you have a continuous flow of lithium. I think I'm right on that. So that has to be developed. And then that heat exchanger then has some fluid in it that goes to a generator that will generate the electricity. So that's ultimately what you want. ITER will not generate any electricity. ITER is just for the purposes we've just talked about. DEMO should. And to me anyway, you don't wait until you find out if ITER works. You start on DEMO now. And indeed, people are actually, I think we have to, at Princeton, they're working on the spherical tokamak with that in mind. We've had some problems. The spherical tokamak shorted. And you're talking about hundreds of, I don't know how many, 10,000 amps or something of that magnitude. A short at 10,000 amps is one heck of a lightning. I mean, it melted the inner tube interconnect, and I don't know what it did, but it was a disaster. They had to rebuild it. So things happen. And you just try and do the best you can.
Are you still actively involved in all this stuff?
No, I'd love to be, but
Your people take up golf.
well, I'm sort of the father of that 20-year plan, and it's now 20 years after, because I did it in 2003 and it's now 2024. And so it's been rather interesting to watch it. And I feel some responsibility. I think had we not made it the top priority, I don't know whether we would have rejoined. As a presidential appointee, have a tremendous responsibility. You actually are there to provide the policy guidance. You have a wonderful group of civil servants that you work with, but it's the presidential appointees that set the policy. So I really stuck my neck out. We wrote the 20-year facility plan. It wasn't without information. All of the advisory committees, very helpful. But everybody knew it was mine. And if it had flopped, everybody would knew that it was mine. So you do the best you can.
How is the heat from the plasma routed to an electric turbine alternator? And he commented that lithium melts at about 186 C.
Unfortunately, there was voices somewhat out of sync. Are you asking how the hot gas drives the generator? Oh, that's through the blanket. The blanket is also a heat exchanger. So I have, I mean, these are gas-fired turbines, and the hot gases are, I don't know what they use. I might use liquid mercury, for example, as a coolant. I don't know what the the heat transfer liquid would be. But whatever it is, once it gets out of the blanket, it goes into a source that creates the steam that drives the generator. Remember, that blanket is really a major issue. There's all kinds of things, and it has to work. So, previous question about steps along the way, that's one of them that they're now working on for just that reason.
So the blanket is a tremendous insulator layer. So what you're saying, right? The blanket is an insulator.
Well, you have an insulating layer outside the blanket, but yes, the blanket, I would call it the heat transfer agency and the tritium generator. that was done. I don't know the answer. The design, the D shape, actually came from General Atomics in San Diego. They had experiment. Everybody, what's your first guess? You make a circular cross section, and there was a theorist at I think it was at General Atomics that showed that it was always unstable. And so they started playing around with different geometries, and they actually built something that looks like ITER. I mean, it's not of that magnitude, but they built a D shape. And they've demonstrated that it's more stable. One of the big issues is called the diverter. Remember that there's no electricity produced by ITER, but you're producing 500 of power. It's got to go somewhere. And so there's an exit. Well, you can use tungsten exit, but it's not trivial. Actually, the diverter design turns out to be very tricky. Another step, Bob, as you described, along the way. And there are some now new designs for the diverter that we think work. Yes. Yes. Yeah, somebody wrote, Bob wrote, lithium melts at 186 Celsius. That'll be very interesting to see how you get a flow of liquid lithium in the front or in the blanket itself. You can actually, if you want to explore this, I would urge you to go to the website of PPPL, the Princeton Plasma Physics Laboratory. And they talk about all of the things that we just described. Yes.
Any other questions from the audience? Here and also the Zoom. Let's say thank you to it's quite education for our engineers. It's thank you from the IEEE. Well, we are all different IEEE groups. This one happens to come from the Communication Society, and it's
And I published in the sonics and ultrasonics.
oh yeah.
Great.
Thank you.
Getting published and all that stuff. Retirement is not a great view. Retirement is not.
Oh. No, but I'm being retired. My grant runs out in 2026, and I'm told it will not be renewed.
Okay, thank you, guys.
Thank you. Thank you.
Yeah, actually, we don't have a program nailed down yet in June, but we'll have a speaker in July. She's going to represent NASA, talking about how to explore in the space. Okay, see you in later.
Thank you.
Announcement. Yeah. Okay, bye
Thank you. Bye. Bye. Bye, Kai. Bye. Bye.
Golf and all that.